Hello, welcome to my Lab 5 project. I'm going to be presenting a computational analysis of Felix Baumgartner's historic jump, where he broke the sound barrier in 2012. So, on October 14th, 2012, Baumgartner went up a helium balloon and he entered a free fall that was nearly 39,000 meters. And this lab will analyze the mechanics of that descent. So basically for this, I built a GoScript simulation that accomplishes three goals. So first, we're estimating the proportionality constant for the drag in the drag equation, which is like B. And then second, to evaluate whether our simplified air resistant model is actually appropriate for the altitudes. And then third, we're going to calculate the mechanical energy loss in the fall. And we're going to find the temperature change that he would have experienced in the end. So we had some pretty clear assumptions. We basically had to strip away like the little variables and focus on the forces that matter the most. So we assume that he's represented as a single point mass in this. And we modeled gravitational potential energy using our standard equation, mgh. And we said that the speed of sound will be a constant 343 meters per second throughout the whole descent because he's not going that far into like space. And then I modeled the air resistance, the drag force, which is proportional to the square of his velocity and multiplied by b. So the fundamental physics principle during this is Newton's second law, which we've been working with, and it states that the net force on the object dictates its change in velocity. So in our code, this allows us to basically update Baumgartner's position and his velocity over really small time steps, and at every step we're going to calculate the downward force of gravity and subtract from the upward drag force. And then by recalculating this net force in the loop, we can generate a really highly accurate trajectory of his descent based on all these different parameters. So yeah, you can actually see that's the photo of him going. But if you look at the actual telemetry data from his mission, it was called Stratos. The combined mass of Felix and his pressure suit was 110 kilograms, so that's a point mass. He stepped out the capsule at a launch height of 38,696 meters, and during freefall he got a maximum velocity of 377 meters per second. So he did break the sound barrier at around 30,000 meters and after 40 seconds. He stayed until freefall until he deployed his parachute at around 2,500 meters, and that was 259 seconds after his launch. So here's some of the code analysis. We basically needed the proportionality constant B, and this is kind of fine through trial and error to match the actual values that we got from the actual jump. And basically, then we got terminal velocity, which is when the pull of gravity exactly balanced the upward part of drag. So there's net zero force and constant speed. So since we knew his maximum speed was at 377 meters per second, I just kept adjusting the constant b in my code until that simulated velocity graph had an asymptote exactly at 377, as you can see on the bottom right. And here, if you actually want to run the code, it basically shows, yeah. And then this part here, if you zoom in, little simulation. Anyway, so this brings us to a question that, is a standard air resistant model actually appropriate? And if we're comparing the solution to the real data, the model is pretty close but a little flawed, and basically that's happening because the atmosphere is not uniform. The standard drag equation assumes that there's constant air density, but since the stratosphere has a little bit of air, there's less drag force. And so the constant drag coefficient, it's not constant. So it's undercompensating for the really thin air at the top of the stratosphere. So that's why he accelerated faster at the start. And then also I analyzed the thermodynamics of the jump. So using the energy principle, the initial potential energy was 41.7 million joules, and his potential at the parachute deployment was 2.7 million. So there's a change in potential energy of about negative 39 million joules. At his terminal velocity of 377 meters per second, his final kinetic energy was 7.8 million joules, and the missing mechanical energy, over 31 million joules, was converted into thermal energy. So he increased temperature by about 32 million joules, which is about 200 degrees Kelvin. So yeah, good thing he has a great spacesuit. And that's all.